because our function f is differentiable on the whole R, and therefore it's differentiable on AB closed, on AB open, and continuous on AB closed. There is C in AB such that f prime of C is 0. Okay, that's what the mean value theorem tells us. And f prime of C is what? What's f prime of x? Well, it's simply 7x to the 6 plus 5. So this thing is always larger than 5 because I have a positive term here, and I cannot go below 5, therefore it cannot be equal to 0. And we have our contradiction. Okay, so f prime is never 0. So we get a contradiction. And therefore, we have at most one solution. So now we know that we have at least one solution and at most one solution. The only way the two can happen if we must have exactly one solution. Okay? Therefore, by putting together that the mean value theorem gives us at most one solution, the intermediate value theorem gives us at least one solution, we know now that there is exactly one solution. Questions? Nine. So we assume that f is differentiable on I, therefore f is differentiable on xy open and continuous on xy closed. Because x and y are in I, and f is differentiable on I. So we know we can say that. Then f of x minus f of y is going to be x minus f prime of c times x minus y. So you write this without the absolute values. Okay, you cannot get the absolute values directly with a mean value because it would complicate matters, and absolute value is not differentiable anyway. So you don't want to put absolute values at this point. I mean, you first do the mean value theorem, then you put absolute values. Okay, if two numbers are equal, their absolute values are equal too. That's because absolute value is a function. It assigns only one number. So therefore, these two must be equal. And now we are basically done because this is equal to f prime c times x minus y, which is smaller than mx minus y. And that's going to be the pattern with using the mean value theorem to get inequalities. Every time you use the mean value theorem, you get something which is more precise, which is seemingly more precise, because it gives you an equality. But you don't know the c. It's true for some c. You can't do much with that information. That's why you want to get rid of the c and get something here which depends only on x and y. This is a better information in some sense, because it gives you some relation between what happens to f of x minus fy compared to x minus y. And you don't have any extraneous c that you don't control, which is somewhere. Every time you use the mean value theorem, Rolle's theorem, whatever, check your hypothesis. Okay, you don't check your hypothesis, you are going to lose points. Number 10. So you're told that f prime of x is less than g prime of x for all x in, is it in I? Where is it? Oh. I think I mean in R here. But anyway, so if we have x positive, so first things f prime, yeah, okay. So we are going to say that h is f minus g, and therefore h prime is f prime minus g prime, and that's negative on R, which tells us that h is a decreasing function. So if I take x positive, then h of x must be less than h of 0. Okay, by application of decreasing. H of x is f of x minus g of x, and h of 0 is f of 0 minus g of 0. So that's how we get this inequality. So we can write that f of x minus f of 0 is less than g of x minus g of 0. Okay? Now, b is for negative x. Yes. And then we would again write that the h of x is bigger than h of 0 this time. Okay? Again, it's decreasing, so I must reverse my inequality every time I take h on both sides. That's what it means to be decreasing. And we are going to have a reverse inequality, therefore. I know that some of you have used the mean value theorem to do this, and you can do that, but be careful. In order to use, you need to have the same C, that's the problem, for f and for g. But the Cauchy mean value theorem gives you the same C. But you need to say that. You need to say that you are using the Cauchy mean value theorem. Because if you are just using the Lagrange mean value theorem, the usual mean value theorem, there is no reason to take the same C. It just tells you there is a number. And you have two different C's a priori. You need to show that. So for 11, we take the function f to be x to the r, and okay, and we didn't see that. I should have told you that f prime of x is of course rxr minus 1. For x on 0 infinity. We're looking at the function on positive reals only, and you may have trouble at 0, as you know, okay? Because when you do r equal half, you get square root of x, for instance, and you know that you have a vertical tangent at 0. And anyway, the way we have defined differentiability, we need the point to be an interior point. Okay, we haven't talked about half derivatives at the endpoint, so we don't really, it's not really a big problem. And we are assuming that r is bigger than 1 in this problem. Okay. So we write that f is differentiable on, so I'm doing this on x, y, and x and y are positive, and continuous on x, y. Because that's where we are going to apply the mean value theorem. So we get f of y minus f of x equal to y minus x f prime of c. So that's y minus x r c r minus 1. So again, same thing as before. We have a c, we don't want it, we are going to get rid of it. And we get rid of it by saying, well, c is between x and y. So c to the r minus 1 is between x to the r minus 1 and y to the r minus 1. Why can I say that?
Increasing on that unit.
It's an increasing function. Is it increasing for every r?
Just 0.
Just r greater than 1.
Yeah, we need r minus 1 to be positive. Otherwise, it's not an increasing function. Okay? Because you would get a negative power. So this is where r bigger than 1 is crucial. Okay? And you need to make a comment here to say that x r to the r minus 1 is an increasing function, and that's what you are using here. We need the upper bound, so we would do this, y r minus 1. And therefore we end up with, so r cr minus 1 is less than y r minus 1. Now y minus x by hypothesis is positive, so we multiply by a positive number, and that's what we get. And we finally get that f of y minus f of x is therefore strictly less than y minus x. I forgot my r here. R y r minus 1, which is what we wanted. Okay, another inequality, 12. And we are talking about positive numbers. So f is differentiable on 0, positive infinity. Actually on minus 1, positive infinity. How do I justify this? Why is this a true statement, that f is differentiable on minus 1, positive infinity? Composition of differentiable functions. Okay? I'm composing 1 plus x, which is a polynomial and is differentiable everywhere, with square root, which is differentiable on 0, positive infinity. But 1 plus x is positive when x is bigger than minus 1. Okay? So this is the differentiable function by the composition of differentiable functions. And then we use the chain rule to get a derivative, we get 1/2 1 plus x to a minus half times minus 1. So this is 1 over 2 square root of 1 plus x. Now for positive x, we are going to write that f of x minus f of 0 is equal to f prime of c times x. Okay, we can do that since our function is differentiable on this interval. So this is square root of 1 plus x. F of 0 is 1. That's 1 over 2 square root of 1 plus c x. Well, we need to get rid of c, so we look where is our c. C is between 0 and x. So 1 plus c is between 1 and 1 plus x. Square root of 1 plus c, square root of 1 plus x. Why can I take square roots everywhere and not change my inequalities? Square root is a strictly increasing function on the positive. If it's strictly increasing, it shouldn't go down. Okay? So that's what I'm using. And then let's put just 1, is less than 1 over square root of 1 plus c, which is less than 1 over, no, it's the other way. 1 plus x. Why can I do this? The inverse is decreasing on the positives. Okay? So we are using that 1 over x is the decreasing function on the positive numbers. Fine. So now we can say, what do we want here? We want to say that, okay, then we are going to multiply this by x over 2 so that we get x over 2 here, x over 2 here, x over 2 here. Now we are writing things for x possibly 0, so the inequalities become large instead of strict. And we get this. And therefore, square root of 1 plus x minus 1, which is this thing here, is going to be less than x over 2. Not if x is 0. Then you have equality. Right? If x... Oh, it was strictly greater for this? Yeah, then it's all strict. Yeah. Okay? So we get 12 like that, and 13. So we are assuming that if x is in a plus delta, then f prime is positive. And if x is in a minus delta a, f prime is negative. And the question is, find that f has a local minimum. Well, yeah, because it's decreasing. So maybe let's write this like this. X, a minus delta is here, a is here, a plus delta is here. F prime is this line and f is this line. And here we have negative, positive, so it's decreasing and then increasing. So it's clear that we need to have a minimum. Let's prove it. Let's first take x in a plus delta. Because it's differentiable, we can write that f of a minus f of x is a minus x f prime of c for some c in a plus delta ax. But on this side, f prime of c is positive. So a minus x times f prime of c is negative, and f of a minus f of x is going to be negative, meaning that f of a is less than f of x for all x in a plus delta. Now we do the other side. So we take x in a minus delta a, and we write that f of a minus f of x is f prime of d a minus x for some d in ax or x xa. And this time we have that f prime of d is negative, a minus x is positive, so when we multiply it's still negative, and therefore f of a minus f of x is negative. So we get that f of a is less than f of x. Is f prime necessarily 0 at a? 1 in favor? 2? You dissent?
No. Because it may not be differentiable.
Exactly. You can do the whole problem exactly. Everything we did works if it's differentiable except at a, like the absolute value. Okay, so you could do exactly what we just did, and everything applies, because the mean value theorem doesn't ask you to be differentiable at a. It only asks you for continuous. Okay, so you write everything, and it's fine, and everything applies, and you do get a minimum, but you don't get a horizontal tangent here.
But in the statement of the problem, it was differentiable. Differentiable over the integral.
Yes. But we could do a better problem by dropping this hypothesis. Okay?
Wait, doesn't the mean value theorem say it's differentiable on that interval though?
No, because what I'm doing is using the mean value theorem between a and x. 'X. So I need continuity in AX closed.
Oh, okay.
So I need continuity in AX closed. 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 So I need continuity in AX clos Okay? And I need differentiability on AX open. So it may be that it's not differentiable at A. So that's one remark. And what happens in fact is that, well, in an example like this, you have that your f prime is not defined at A. So that's why. But what may happen is that your f prime is defined at A but not continuous. And therefore you go from minus to plus and you jump. But that's not really possible actually. Okay, so yeah. So this is only this is really the typical example where you would use something like that. Other questions? Yeah, a property which I think I talk about in 5.4, and if I have not, I should have, is that the function f prime, there is no guarantee for it to be continuous. However, if a function is the derivative of something, like f prime, it has the intermediate value theorem. So it's not necessarily continuous, but it takes all intermediate values. Okay, it may jump, but it still needs to take all values between 2 points. Okay. Did you have any questions on this chapter, or this type of problems?
Would you repeat what you just said?
That f prime, so assume that your f prime is defined on AB. And assume that f prime of A is negative and f prime of B is positive. Then there is a C in AB such that f prime of C is 0. So I'm writing down the intermediate value conclusion. But what's remarkable here is that I don't need the hypothesis. The hypothesis is my function needs to be continuous. Well, not if it's a derivative. Because the fact that it's a derivative gives it some type of regularity, okay, which is weaker than continuity, but still good enough to have this property. So, for instance, how can this happen for a function which is not continuous? Well, it could be a function like this, which does this, and then this. You have a jump here, but you see it covers everything. Okay, there is no, your range is an interval. This is what we're saying. Even though you have a discontinuity. Okay, so these are some of the more subtle properties that I talk about in 5.4. A day of blizzard, you can decide to look at this. So let's go on with 6.1. So let me remind you a little bit what we did last time. We defined so we assume that our f is bounded on a closed and bounded interval AB. And we define the lower Darboux sums like this, and the upper Darboux sum like this. Actually, it's xi minus 1. Okay, for a partition P, which is a set of points, x0 equal A, and then xn equal B. So you discretize your interval AB. You pick n plus 1 points. You cannot pick the two extreme points. The two extreme points must be A and B. And then you form these rectangles. For the lower Darboux sum, you take the smallest, you take the greatest lower bound of your function on the interval, xi minus 1 xi. For the upper one, you take the least upper bound. And that gives you your Darboux sums. And you can do that for any bounded function, because then these numbers are defined, are finite. Okay, as we said. Now, we'll say that a function is Riemann integrable if for every epsilon you can find a partition such that the difference between the lower and the upper Darboux sum can be squeezed between 0 and epsilon. I know I put a large inequality in my definition, in my notes. It doesn't matter really, but since we have used strict inequality with epsilon, let's be consistent. So we say that our function is integrable if we can really get the two upper and lower Darboux sums to be arbitrarily close. And our integral will be the thing which is squeezed in between. Okay, that's how we are going to define our number, what the integral of f is. So last time what we did is, I think we took a constant function and we showed, well, this is going to be integrable because the upper and the lower Darboux sums are the same. So you get 0, and 0 is less than epsilon. Okay, that was quite easy. Now, can we find a simple example of something which is not integrable? And the answer is yes. Let's do this now. Take the following function, define f of x to be 1 if x is rational, and to be 0 if x is, if x is not rational, and let's take x in 0, 1. Okay, so the function is defined on 0, 1. Okay, because we want to close unbounded interval. So this is a nice bounded function, but you can tell it's going to jump a lot because of the density of the rationals. Okay, whatever interval I'm going to take, I'm going to have values where my f is 0 and values where my f is 1. However, and that was a motivation to get a better integral than the Riemann integral. But to see that one, you have to wait a couple of analysis courses. But anyway, so that you don't die with expectation, meanwhile, let me tell you a little bit what happens is that because you have all these jumps on a countable set, the other integral, the better integral, which is the Lebesgue integral, is going to say, well, I don't care about countable sets. This has measure 0, and therefore my integral is 0, and this is an integrable function. Okay, so that will be one of the motivations why you need something better than the Riemann integral. However, the Riemann integral is not that bad in the sense that it coincides with a more general integral for many functions. So it's not like you have to throw this away and construct something completely different. No, it's the same thing. The only thing is that it needs to be extended so that things like that don't happen for this other integral. Anyway, so let's show that this is not integrable. So f is not integrable, and it's quite easy to see why. So take any P, any partition P. I claim that the lower bound, well, the greatest lower bound, but any lower bound of my function on this thing must be 0. Why? Yes?
Because any two rationals would be an irrational, which means it would be 0 by density of irrational.
Right, it's because I will find R, so by density of irrationals, we can find R between xi minus 1 and xi. And R is rational.
Don't you have to use density of the irrationals?
Yeah, density of irrational.
Oh, that's the way I define things? Okay, yes, thank you. So, well, let's not use R, let's use S. So I find an irrational, and let's say here irrationals. Then f of s is going to be 0, which implies that the minimum, that you do have a minimum, and that this minimum is 0. Now you do exactly a symmetric thing for the maximum, or for any upper bound. You're going to say that this is going to be 1, and this time you are going to argue that by density of the rationals. So the lower Darboux sum is going to be 0 times xi minus xi minus 1. For all terms, we are going to find the lower Darboux sum to be equal to 0. Okay? Because all the lowercase m are 0. So you cannot get anything else. And the upper Darboux sum is going to be 1 here. And this is a telescoping sum, okay? So what's left is the first and the last term. Maybe we should write it the first time. So when I do I equal 1, what do I get? x1 minus x0. Then I do I equal 2, and I have x2 minus x1. And so on, all the way to xn minus 1. So So what's going to happen is that x1 cancels with x1, x2 with minus x2, xn minus 1 with minus xn minus 1, and you're left with xn minus x0. Okay, we are going to use this trick many times. When you have telescoping sums, that's what you do. So you get xn minus x0. What is xn minus x0? 1. Okay? Because xn is 1 and x0 is 0, according to, a and b are 0 and 1 here. So we get 1. So now, of course, if you pick epsilon equal half, you see that UF of P minus LF of P is bigger than half because it's 1, and for all P. So you cannot get them closer than 1. Therefore, your function is not Riemann integral. Okay, did you follow that? So every time you cannot get your Darboux sums to get as close as you want together, your function is not going to be Riemann integral. So now let's check another important property. Monotone bounded functions on AB are Riemann integral. You see that this example, which is very simple, where I take 1 when I get a rational, 0 when I get an irrational, cannot be monotone anywhere. You take a very small interval, it's all full of rationals and irrationals, so it's going to jump around, and you're never going to have some monotonicity. So, okay, that's not very difficult to show. Okay. So in order to make this work, and what am I going to do? Yeah, we are. Let's assume that f is increasing. A monotone means either increasing or decreasing. We're going to do the proof for increasing, and I'll let you do the proof for decreasing in the homework. And so let epsilon be any strictly positive number, as always, and pick a natural n, such that b minus a over n times f of b minus f of a is less than epsilon. How do I know that I can find such an n? Yes, it's the Archimedean property. Right? It's the Archimedean property because this is equivalent to n being bigger than b minus a f b minus f of a over epsilon. Okay, so if I can find n doing this, then of course I'll have this. Okay, so n exists by the Archimedean property. Fine. Now my definition says that for any epsilon I must be able to find one partition such that the upper minus the lower is less than epsilon. Okay, so I just need to find one. And my favorite one in general, when I'm asked to find one, is the simplest possible one, which is where all the points are equal distance. Okay, so I'm going to define the partition by doing x0 equal a, of course, and then x1 equal a plus b minus a over n, and x2 will be a plus 2ba minus a over n, and so on, and xn is going to be a plus n b minus a over n, which is b. Okay, so I keep using the step b minus a over n, and you see that the distance between 2 points is always b minus a over n for this partition, which makes things nicer. And n has been picked quite big normally because it depends on epsilon, and it increases as the inverse of epsilon. So the smaller your epsilon, the bigger the n. So what we observe here is that xi minus xi minus 1 is always b minus a over n for all I. So that's one thing. Now we compute the lower Darboux sum. Which by definition is this thing. Now what's going to be the greatest lower bound on the interval xi minus 1 xi of the function f which is assumed to be increasing? How low can you get with an increasing function on the interval xi minus 1 xi? F of xi minus 1. That's going to be your lower bound, and it has to be the greatest lower bound because it's a minimum actually. So this thing is f of xi minus 1. Okay, so that's the big simplification that we get. We can explicitly compute our lowercase m and our uppercase m in this case. Now this guy we say is b minus a over n. So our lower fp is b minus a over n sum from I equal 1 to n of f of xi minus 1. Now the upper m, the upper Darboux sum, is of course going to be f of xi. Okay, that's what you're going to get. So you get exactly the same formula, but this time it's f of xi instead of f of xi minus 1, b minus a over n. then we do the difference. The difference is the sum. We can pull out this b minus a over n out, and that's the point of taking an equidistant partition. And then we'll have f of xi minus f of xi minus 1. Am I going too fast, or you are at the stage where you don't care anymore? So I'm just doing some algebra, okay? I have f of xi minus 1 here. I have f of xi here. I'm doing the subtraction, that's why I get this. That's all. This is again a telescoping sum. Okay? So we get the first and the last term. So this is b minus a over n, f of b minus f of a. And now you see why I picked my n to be what it was. Because this is precisely less than epsilon. Of course, as always, I cheated. I first did the computation and then pretended that I hadn't done it. But that's how you find the ends. So this is less than epsilon, and we are done. We have found a partition such that the upper minus the lower Garbus sums is less than epsilon. You don't seem that impressed, but Okay. Okay, the next task is going to also show that continuous functions are Riemann integrable. And that's worse than this, a lot worse. And I'll explain to you why, but next time we talk about this. And probably I'll wave my hands and explain to you why it's bad. But it's not that bad, but it takes a little time to do it. So maybe we should stop here for today.